welcome to our annual dinner. I'm very pleased we all made it. We found the salon and so on. I'm going to turn over our dinner to our host in just a second. But as a organization, just a little bit of ceremony to go through. First of all, since we are the RASC, Royal Astronomical Society, we were incorporated in March the 3rd, 1903, and it was King Edward VII that gave us the designation royal. So in that mode, I would ask you to stand, and we will toast the Queen. Ladies and gentlemen, and yes, happy birthday, Charlie. To the Queen. Also, as a note, that the Ottawa Centre incorporated in 1906. So, as you've probably noticed, I'm wearing a little bit of a sailor rig here. And a part of the ceremony with the Navy is we have daily toasts. And, well, yes, there's that too. There is that too. I forgot about that. But as I mentioned, daily toast. The Friday toast is to wives and sweethearts. And somebody in the crowd always says, "May they never meet." But I'm just going to switch a slide here. In the time of the season, this is an astronomical a little connection as well. On the 11th at 11 o'clock, the sun actually does shine on the unknown tomb in the War Museum. When it's not cloudy. When it's not cloudy, that's true. And in commemoration of that, and as your president, I'm going to invoke our Military Sunday toast. But first, I would request a moment of silence to remember our missing comrades. Thank you, and with that, I will toast the Sunday toast from the military. Please toast missing comrades. Okay, as I mentioned in the past, being president of this organization, looking back on the history of it, I want to thank you for giving me the honor of being your president. And in actuality, it's one of the easiest jobs in the world because there's so much professionalism in this outfit that all we have to do is say there's a project available and bang, it's done. And this year's guest speaker is no exception. Brian McCullough was the person that took over the task, and we hit a home run, Brian. And at this point, I'd like to introduce our chair and our speaker introducer, Brian McCullough.
Thank you. Let's bring that down to a more reasonable level. It's a really great pleasure to be able to introduce our speaker for this evening, Professor Phillip Stooke from the University of Western Ontario. And he was actually recommended by Bridget and my daughter Emily, who's studying at Western as well, and she's heard Professor Stooke speak before, and so he came with a high recommendation, so we'll live up to it, buddy, all right? Phil Stooke did his undergraduate work and his PhD at the University of Victoria, and did his PhD thesis, and it was on mapping asteroids. And this is a work that's continued throughout his career. At University of Western Ontario, he's an associate professor of Faculty of Geography, and he's got a cross connection to the Faculty of Physics and Astronomy. So he's been working on cartography and planetary science, or his strong suits, we could say. Some of the achievements he's had over the past number of years, he's done a global photo mosaic map of the asteroid Eros, and I think that still stands apparently as the best of its type to date. He's involved with cartography of non-spherical worlds. And I think if you, he's also just published a book, The International Atlas of Lunar Exploration. And I think if you have a read through that, you're going to see a lot of the work that he's been involved with. We'll see some of that here this evening. And he'll be continuing, I guess you're doing an update on that book as well, and you're going to be doing a similar book on Mars. He's been involved in mapping small bodies, the satellites of Mars, Jupiter, Saturn, Uranus, and Neptune. Interesting stuff, too. I mean, beyond that, mapping the nucleus of Comet Halley. All right? I'd like to know how you did that, but all right. He was involved in helping to locate the Viking 2 lander on Mars. He helped locate the actual landing site for that spacecraft. And he's also been doing that with other spacecraft on Mars and the Moon. So talking about his book updates that are coming, keep an eye out for those. But something quite special happened, I guess it was earlier this year, that he got a phone call from a friend to let him know that asteroid 172996 Stooke has been named in his honor. So Phil Stooke, the floor is yours.
Yes, I wanted asteroid 1, but it was already taken. Okay, so exploring the moon past and present. This has really been my life since I was a teenager. At the time of the Apollo missions, I've been interested ever since, and somehow or other I got lucky enough to turn it into a career, so I feel very happy about that. And the map in the background here, I made that map a few months ago. That's a combination of shaded relief by the US Geological Survey and albedo, light and dark markings from the Clementine mission. And I plotted on it all the things that had landed or impacted on the surface. And I made it a few months ago, and it's already out of date because something happened today. At least I hope it did. I haven't actually heard the news yet. But if everything went according to plan, then the Indian spacecraft Chandrayaan actually deposited its moon impact probe on the moon today. So now I have to change my map. Of course, it should have hit at the South Pole, which isn't quite covered in this, but I have to update my map anyway. Okay, can I have the next slide, please? So yeah, this is the cover of my book. It was just published at the end of last year, about a year ago. It took me about five years or thereabouts to put it all together. And so what I'm going to do is to talk about some of the things that I had to do to make this happen, to make my Atlas of Lunar Exploration happen, some of the stories that came out of the work that I did for that. Next slide, please. And I will say something briefly about where things are going if I don't run out of time. So, of course, you could ask, hasn't this been done before? I mean, people have been writing about Apollo and about the moon and so on for several decades now. And I would like to put in a plug, actually, for an excellent book for people who are interested in this kind of thing, a book by Don Wilhelms called To a Rocky Moon, which tells the story of, well, basically the way that geologists stole the moon from astronomers. Yes. I have a background in geology and cartography. I'm not an astronomer, and there's going to be very little astronomy, if any, in this talk. So if you want to leave now, that's fine. But hasn't it all been done before? Well, no, the answer is it hasn't all been done before, because if you actually start looking through all the things that have been said about lunar exploration, there are a lot of gaps. And one of the goals in my book was to try to fill in some of those gaps. So I'm going to show some of those and describe the kind of work that I was doing there. For instance, the panoramic photos that the Surveyor spacecraft took on the moon. The Surveyors were robots that landed before Apollo. They took pictures, but if you went searching around for anything other than the most cursory coverage of those pictures, it was very difficult to find. So I've tried to address that issue by actually putting together big photographic panoramas of the Surveyor landing sites, and that hadn't really been done before. Then there's a whole story of landing site selection for Apollo and also for Surveyor and for the Ranger impact probes before that and so on. A lot of the book is about landing site selection, so I'm going to just pull a few stories out about that. And then there's the question of what the Russians did on the moon, that's something, there are a lot of details there have never been fully recounted, and they're certainly not fully recounted now in what I've done, but I have been able to fill in a few gaps here and there. So really what I'm looking at with my book is quite a lot of history. And for history, you have to go to the right sources, and there are all sorts of things. There are obscure journals and technical reports and so on, what some people call the grey literature, which is published, but it's difficult to find. So I wanted to pull things together from these kinds of sources and put them all into one handy reference book. And then there are things like committee minutes. One of the things that triggered this was going to the library at the Lunar and Planetary Institute in Houston and seeing the minutes of the committee that chose the Apollo landing sites, just full of interesting information. But you want to go through and synthesize it all and summarize it. So that's in my book. There are archives that I had to dig around in to find memos and reports and that kind of thing. Soviet sources, I went to Russia a couple of times, and it's still possible to talk to the people who are involved in this work, or many of them. And of course, as time goes on, that becomes more and more difficult. So it's good to get that done now. This map, I should say, is a map of one of the Russian landing sites, the Lunokhod 2 landing site on the moon, something which has never actually been published in full in the West, and actually not really published in full even in Russia. They ran out of money before they could publish the big book describing that mission. Next slide, please. So let me start off with just one of these things then. This is right back at the beginning of the American assault on the moon that ended with Apollo. One of the first things that they did was to send spacecraft that would just crash on the moon, but take photographs on the way down. The final photos in those sequences were much more detailed than we could ever see through a telescope. So this gave us our first close-up look at the moon. But if you're going to do that, how do you choose the points where the impacts will be made? So I'm just mentioning this to show one of the kinds of work that I had to do. And in this case, I was able to talk to the person who did the work, a rather well-known person from astronomy in those days, Ewan Whittaker. He worked, well, first he was with the British Astronomical Association in England, but then he came to the States and worked with Gerard Kuiper on the big photographic atlases of the moon. He chose the impact sites for Ranger. So I had a very nice visit with him down in Tucson, and he showed me lots of interesting things there and gave me this, this information about site selection for Project Ranger. You're going to smash something into the moon, but take pictures on the way down. So where are you going to do that? Well, what they had to do was to make sure that the lighting was right. So on any given day during the potential period that you could impact the moon, when the lighting would be right, on any given day, the terminator, the line between light and dark, will be in a certain place. And you don't want to impact there because there's a good chance that you'd hit in a shadow somewhere and your closest pictures would be dark. So you actually plan the landing sites to be some distance onto the lit side of the moon. So for any given day, he would mark where the terminator was and then choose a potential zone of impact sites that were about 20 degrees of longitude away from the terminator, where the lighting would be okay for the photography. You draw that line down, and then you have to look for suitable places along it. And they chose relatively smooth places that might be suitable for Apollo landings. So he gave me the map that showed this scattering of points, and they're not really randomly scattered. They actually lie on approximately on north-south lines, 20 degrees west of the terminator on the days during that impact period. And they chose one of them for the landing site, and at the bottom we see some of the Ranger pictures that zoomed in on that point. So the basic thing here is that I had to go back to the people who originally did that work for some of the things I did. So I had the pleasure of meeting some interesting people in the States and in Russia who worked on these things. Okay, next slide, please. Another thing I wanted to do was to represent the surveyor landing sites. Lots of people have made panoramic photos of the Apollo landing sites. The astronauts would stand on the moon, They have a camera strapped to their chest, and they would take a photograph and then turn a bit and take another, turn a bit and take another, and they would go all the way around and take pictures around them. And people have assembled those into panoramic photos of the lunar surface. Well, Surveyor was a robot, so it just sat there and looked around and took lots of pictures. And this was in 1966, 67, the last one, early in 68, before Apollo. And this is what the panoramas looked like. It took several hundred photos to cover an entire panorama. And when you put them together, well, this is what you get. Not really a very attractive looking panorama, because we have these very marked contrast steps from one picture to another. The seams in the mosaic are so visible that they really overpower the mosaic, and you can't see the scene behind them properly. So I wanted to fix that. So the first step is that you've actually got to go and find all those pictures. Now, you could go and find all the individual pictures and try to mosaic them. I didn't have time for that. So what I did was to take mosaics that had already been prepared. So mosaics like this one that had already been prepared by the Jet Propulsion Lab and by the US Geological Survey. They'd make it by hand, piecing the photos together on a big wall. In fact, some of them were done inside spherical bowls, so they could photograph them with a more precise geometry. So they'd put the mosaics together and then photograph them. And I could find the photographs of pre-assembled mosaics like that, but with all of these visible seams. Well, you've got to find those photos, though. I had to go to the Lunar and Planetary Institute in Houston, the Lunar and Planetary Lab at the University of Arizona in Tucson, and to the US Geological Survey in Flagstaff, where a lot of this work was done, before I could find the full set of mosaics like that. And then they have to be cleaned up. And how do we do that? We use Photoshop. Good old Photoshop. And in Photoshop, I would trace around each individual polygon that represents one of those frames and copy it out of the picture and paste it over itself. And now it's a separate little thing floating above the mosaic, and I can brighten the dark side of it and darken the bright side of it and remove any other little problems that there might be in the image. Any, some of them have dust spots on them and things like that. And then paste it back down onto itself, but it's been modified so that the seams are removed. And I had to do that individually for every frame, hundreds of frames on each one. So each of these panoramas took about 3 months to clean up. But the result is that you can actually see the lunar landscape. So can we have the next slide, please, there? And I'm going to go through these fairly quickly. This is the Surveyor 1 site, the first American soft landing on the moon. The Russians had one just a few months earlier, which we're going to look at in a minute. But this was the first American site, and I've got a picture there, a long shadow being cast by the setting sun in that picture. Let's just go to the next picture, please. And that shows part of the landing site. So originally this had all those horrible visible seams across it, and they've been removed. And you can see some little mountains on the horizon there. Can we have the next picture, please? This is a close-up of some of those mountains. So these were actually quite good landings on the moon. We got quite good data sets from them, but they just haven't been seen very much. So I thought that it was quite useful to be able to clean those things up and have them for the book. And they're also available online. The Planetary Society has these on its website if you want to look at them. Next slide, please. And we can play tricks that they couldn't do back in the 60s. Here's the panorama. A Surveyor 1 wrapped around in a circle, and you can see there's a little bit missing where the spacecraft got in the way. But basically, we can make much better maps of these landing sites today than they could back in the 60s, because we can play these kind of little digital tricks with the pictures so much more easily. So that's the Surveyor 1 landing site there. And let's go on to the next one. And that's a nice panorama, but they're not all quite as nice as that. This is Surveyor 3. Surveyor 3 had some really difficult problems. It threw up a lot of dust when it landed. There was dust on the in the camera system. So some of the pictures have they're clear on one side but foggy on the other side because of dust. So they're really not as good. And also, the only complete mosaic was taken with the sun quite high in the sky, so it's not casting shadows. So we get a very bland-looking panorama. It does look better when you zoom in on it, I have to say. But this was the first time that a robotic arm was used on the moon or any other world. Some people will have been looking at pictures of the Phoenix lander on Mars over the last 5 months. The mission just came to an end. But for 5 months before that, a robotic arm was digging trenches on Mars. So we've just been watching that happen. But this was the first robotic arm ever used on another world, the first trenches dug in the surface of another world, early in 1967. And let's just go to the next slide, please. And this is a close-up of those trenches, then the first ever dug on the moon. That thing on the left is the shadow of an antenna. But then we've got the two trenches, one of them that's kept quite sharply defined walls, and the other one that's kind of collapsed a bit. And if you look just up in the upper left, there are several little dark lines with little spots at the end of them. And those are actually stones that were set rolling across the surface by the exhaust of the rockets as Surveyor 3 landed on the moon. The exhaust blew those little stones and they left little trails as they rolled along. So not great pictures, but they do help to tell part of the story of the history of lunar exploration like that. Let's go on to the next one, please. This is Surveyor 5, and I think we'll just pass on to the next one. Surveyor 6. Again, the sun is quite high here, but that helps to show up some rather funny dark splotches on the left-hand side, sort of just left of center there. There's a footpad that you can see just to the right of center at the bottom. This spacecraft, Surveyor 6, it landed on the moon, took lots of photographs, it made a chemical measurement, it measured the chemistry of the lunar surface with an ingenious little instrument, and then they fired the thrusters again to lift it up, and it jumped up and it hopped a little bit and it flopped back down on the surface. And this picture was taken just after that, so this mosaic was made just after it. So those dark splotches are actually the marks made by the thrusters as the spacecraft was hopped off across the surface. So can we go to the next picture, please? And this is a map made by taking that panorama again and wrapping it around in a circle. The two things that I've marked with the letter F are the footpad imprints that were made when the spacecraft first landed. And there would have been a third one, which is under the spacecraft, so we can't see it. And then there are three other little marks that I've marked with the letter C. Those were shock absorbers called crushable blocks underneath the Surveyor, which also pressed down on the surface. So when the spacecraft jumped up and flopped down again, it revealed the pattern of the footpad imprints and the crushable block imprints. And we can see the little dark patches made by the thrusters as it made that jump. So again, sort of, this is really a better illustration than was possible at the time of that little story of events on the moon. Can we go to the next one, please? And then probably the most interesting of all these landings was Surveyor 7. All the other landings had been designed to support the Apollo program by landing in smooth mare areas, the smooth dark plains of the lunar surface, to help to certify that they were safe for Apollo landings. Surveyor 7 was the only one that was freed to go off to some scientific site, and they landed just on the north rim of the crater Tycho in the southern highlands. So we're on the ejector blanket of a big fresh lunar crater here. This is the panorama. Let's just zoom in a bit. The next one. Close-up of part of the lunar surface there, boulder fields. There are a couple of boulder fields sort of up near the horizon, which are around the rims of craters that are tilted away a little bit in a valley. We don't see the crater, but we see the boulders around the rims. And it's from seeing features like that off in the distance and measuring the azimuth, the angle towards them, that we can actually locate these spacecraft. And that can be done more accurately now than it could be back then. Let's go to the next one, please. And this is seen just looking north from Surveyor 7, and this rather rugged and I think very beautiful ejector blanket of the crater Tycho, looking out across an area where huge amounts of loose debris and also impact melt were deposited on the surface immediately after the impact. And some of that stuff was fluid enough to flow down the side of a hill off in the distance there, creating little gully-like features that look a little bit like gullies on Mars, but these were certainly not cut by flowing water. That was flowing impact melt on the surface. Can we just go to the next one, please? We'll get a little close-up of that. So that's the moon, and I like to think that this is the moon as it hasn't actually been seen properly before, because these pictures really just weren't available to us. If you suddenly have the ambition to do this kind of thing yourself, you can pop down to the Lunar and Planetary Institute in Houston, and they have 80,000 surveyor photos just sitting there waiting for somebody to mosaic them like this. So, so go to it. Okay, next one, please. Now let's move on and talk about Apollo landing site selection. A big part of what I did was associated with studies of site selection, and right now I'm extending that to Mars as well, and studying the site selection process for all the different landers on Mars. But when we deal with Mars today, we have an embarrassment of data. We have fabulous pictures, pictures with 25 centimeter resolution on the surface of Mars, global maps, compositional data, just an embarrassment of riches in Mars data at the moment. But they certainly didn't have that for Apollo. So when they started planning site selection for Apollo, well, how would you go about it? The sensible thing might be to photograph huge areas of the moon at high resolution and then look through all that stuff looking for the best sites. But back then in the 60s, they didn't have the resources, they didn't have the capabilities on the spacecraft, and they didn't have the capability to transmit it all down to the ground, or even the capability to analyze it all that we have today. So they couldn't photograph huge areas and look for the best sites. They had to do a major process of down selection first, which was just done by telescope. So you look through a telescope and you find what look like smooth spots, despite the fact that you simply cannot see enough in the pictures to know whether they're smooth or not. But people had a theory. The theory was, if the surface is dark, it will be smooth, and if it's light, it will be rough. That was the idea. And the justification for it was, well, we know that the highlands are lighter and they're rougher, covered with craters anyway, but on the plains, the mare areas of the moon, they're covered with light streaks, the crater rays, which spread out from impact craters. So they thought that those rays would be pitted with secondary craters or splattered with rubble, ejecta thrown out of the craters. So they would be rougher. So if you chose areas with no rays, they would be the smoother places. So that was the justification. So initially, people went through, and this particular slide here, which is just showing the equatorial region of the near side of the moon, shows about 15 places that were selected as possible landing sites on the basis of these kinds of rather dubious arguments. Some areas would be smoother than others. Now let's go to the next one, please. And while people were thinking things like that, they were also daydreaming about great things that people could potentially do on the moon, which still haven't come to pass. Long traverses, the idea of astronauts landing on the moon and maybe spending 6 months driving around in big Winnebago-type pressurized rovers, exploring for hundreds or thousands of kilometers. So this was from a study in 1965 showing possible traverses on the moon. Let's go to the next one, please. And more. These are all in the area of the crater Kepler, which any moon observers among you might know, a nice fresh rayed crater not too far from Copernicus, which is probably better known. But this was actually the part of the moon, the first part of the moon that was covered by detailed geological maps made by the US Geological Survey. Is it okay to use that expression, geological, for the moon? There used to be a lot of argument about that. Of course, does geo mean the planet Earth? I prefer to think that it means land. And so it can apply to the land on the moon as well. But obviously some people would disagree with that. And so they say, well, you should call it selenological. The trouble with that argument, though, is that now, look at us now, we've looked at 50 or 60 worlds in detail, when you include all asteroids and the moons of the outer solar system and so on. Have we got to have a different term for every one? It doesn't make sense. So we'll stick with geological and apply it to everything. And that's not really my argument. That's an argument that was promoted years ago, but still people sometimes argue about it. Okay, so this was the first geological map of part of the near side of the moon that was published by the US Geological Survey. And as soon as you had a geological map, people could start planning geological traverses. They'd drive around and make sure that they visited lots of different kinds of material. So these were various plans among lots of others that were published at the same time and for the same place, showing how people might do geological exploration on the moon. So all this kind of thing is going on all the time while the engineers are still building the spacecraft. Let's go to the next one, please. This is the next step in Apollo site planning. So what have we got here? In the background, we've got the same map as the one that I showed a couple of slides earlier that showed sites picked from telescopic observations. And in fact, those spots are marked on here. They're in a sort of a grey shade in the background. But on top of that, we've got sites that people have identified as being of interest for future observations. And actually, quite a lot of them do correspond to the old sites, or approximately correspond to the old sites from that earlier study. The black rectangles are lunar orbiter photographic targets. The lunar orbiters orbited the moon, as the name suggests, and photographed the surface looking for Apollo landing sites. And they didn't have the resources to photograph everything, so they had to be very selective, just photographing these small areas, which were chosen on the same lines of argument as in that original telescopic study that I showed a couple of slides earlier, trying to find what look as if they might be smooth areas, and then using these high-resolution photos when they came in to certify them, to tell whether or not they really were smooth. Most of them were hopeless. But a few of them were okay. And the white circles are surveyor landing sites, places that were chosen as potential landing sites for surveyor, some of which correspond to those other landing sites and some of which don't. And in a few places, all of these things come together. So right at the center in the middle one, there's a surveyor landing site with a lunar orbiter rectangle over it, and also one of the little grey lines underneath it, which was one of those original telescopically selected sites. And in fact, that's the place where Surveyor 6 landed. And it's also the place where Surveyor 2 was supposed to land, but it crashed, and where Surveyor 4 was supposed to land, and it crashed. So they really wanted to go to that site, and they managed it with Surveyor 6 in the end. And most of the Surveyor sites were chosen specifically to certify as safe some of the Apollo landing sites. Let's go to the next slide, please. So once Lunar Orbiter was there and could take its photos, we moved into the next stage. Now people finally had high-resolution images for site selection. And these rather crummy little pictures don't do anything to show the quality of these wonderful pictures. They're very, very high-resolution, beautiful pictures. And these days you can get very high-resolution scans of all of them on the Lunar and Planetary Institute's website. But once people had these, they looked for places where they could potentially land. And the way they did that was they took a bit of plastic and they marked out an ellipse on it. And the ellipse was sized, as I say there, about 7.9 by 5.3 kilometers. That was approximately the accuracy with which they thought they could predict where the thing would land as it came in on its trajectory. So those were the landing ellipses. So it was marked out on a bit of a transparent plastic at the right scale for the photos, and people would just move it around on the photo until they found a spot that had very few obstacles in it. A nice smooth-looking area, not too many big craters, no big craters, in fact, not too many little hills or anything like that. And every time they found a place, they would mark it, and it gets a little number on the map here. And then they'd analyze it in more detail. How many small craters are in it? How many boulders can be seen in the highest resolution pictures, and they had to consider other things too. During the approach, you'd be flying in using radar to measure elevation. If you're flying over a very jagged, hilly area or a big crater or something, then it starts to get complicated for the radar and the computer analyzing the radar data to figure out whether it's a safe site. So they had to avoid sites that had obstacles on the approach. So eventually they narrowed it down. So here, the white circles are just places that look smooth enough initially, and the black ones are potential sites that passed a variety of other tests for smoothness and for safety of the approach. And from those, eventually, they were able to find the safe landing sites that they needed. Can we go to the next slide, please? That ellipse on the left-hand side is actually the Apollo 11 landing site, although Apollo 11 actually overshot that a bit and landed a bit downstream. Downwind of it. I can't say downwind on the moon, can I? Down something of it.
Downrange.
Oh, yeah. Brilliant. Yes, downrange, I should have thought of that. And on the left, we've got one of these high-resolution lunar orbiter pictures showing a couple of potential landing sites. The idea wasn't to say this is where we want to go, because they couldn't control that within a few kilometers, but to say, pretty much wherever you go, you could find potentially interesting things to walk around and look at. And so they've shown a couple of candidate sites there and potential routes that would take astronauts by several little craters that they could pick up samples at. The craters are significant because if you think about it, the bigger the crater is, the deeper it excavates lunar material. So if you pick up rocks around a 10-meter diameter crater, and then you pick up rocks around a 30-meter diameter crater, you're getting samples from different depths, and that's what they were interested in here. So they're deliberately choosing routes that take them past several different craters at different sizes. Okay, next, please. So that's a kind of a very brief summary of the way that Apollo landing sites were chosen, especially the early ones. But I want to go into a particular one that is a story that hasn't really been fully told before I did this. And I should set the stage really because this is a story that was told in part and verbally in Don Wilhelm's book, To a Rocky Moon. And I do recommend To a Rocky Moon, fabulous book about the moon. Don Wilhelms tells the story. He was one of the people who chose sites and helped to train the astronauts. So he tells the story. Now, Apollo 11, its goal was to land on the moon and get back safely, to fulfill the requirement that President Kennedy had announced in 1961, to land a man on the moon and return him safely to Earth. Didn't really matter if they were 5 kilometers or 10 kilometers off target, and they were a bit off target. But if you were going to do serious scientific exploration of the moon in future, you had to be able to land within walking distance of the thing you were interested in. And even later when they had a moon rover, they had to be able to land within walking distance in case the rover didn't work. So that was an important requirement. So Apollo 12 was designed to test that. Can we land at, can we make a pinpoint landing? Can we land within walking distance of some scientifically interesting target? So on this map we see the Apollo 11 site on the right, Apollo Landing Site 2, ALS 2. And over on the left, ALS 7 was the Apollo 12 landing site. It's where Surveyor 3 landed. But further off, right on the left-hand edge, is ALS 5, Apollo Landing Site 5, in the Ocean of Storms, Oceanus Procellarum. And there always had to be, for the early Apollo landings, there had to be backup landing sites. Because if you got everybody suited up and in the capsule on the pad and the rocket's fueled, and then there's some little technical problem, it took a while to work through everything and get everything back together again. You couldn't just take off a couple of hours later. So if there was a delay, that delay in fact ran to 48 hours while they unfueled the rocket and refueled it and got everything fixed up again. In that 48 hours, the terminator, the line between light and dark, has moved, and now the lighting isn't right at your original landing site. So you have a backup site that is about 20 degrees further west, following the terminator in the lunar morning. So Apollo 12 was supposed to land at the middle of those sites, Apollo Landing Site 7, but the backup site was Apollo Landing Site 5. And if you just read about Apollo 12, then that's what it will tell you. But this was supposed to be a pinpoint landing. So what's the pinpoint landing in Apollo Landing Site 5? Now, Don Wilhelms tells the story just verbally. He tells that basically the Apollo Site Selection Board asked the US Geological Survey to find suitable candidate sites in Apollo Landing Site 5, and they came up with a list, and one of them was chosen. But what were those candidates, and which one was chosen? So let's go to the next slide, please. So I had to track that down. Don Wilhelms doesn't tell the story, but in the archives of the Johnson Space Center, which are held at the University of Houston Clear Lake, I was able to find the memo that went from the U.S. Geological Survey to the Apollo Site Selection Board, and it identifies 9 candidate landing sites as possible sites. And what are they? They're very small, very fresh craters, very often just a few tens, or well, let's say maybe 50 meters, 100 meters across. Quite small craters, very fresh, surrounded by boulders that have just recently dug up rocks from underneath the surface. So those were the candidate sites, and one of them was chosen. That was identified. So in this memo, they're identified, but they're not identified in a useful way. They're not identified by latitude and longitude, for instance. They were identified as measurements in millimeters on a lunar orbiter photograph. So the next step is to find the lunar orbiter photograph. You find the photo. Is it at the same size those measurements were made on? Well, we hope so. But I had the details. I made the measurements. Sure enough, everyone ends up at a little fresh crater. So we know we've got it right. And the best one, the one that they actually chose, marked at the bottom there, was the Apollo 12 backup landing site. And just to the right of it, there was a cross-shaped pattern of 4 larger subdued craters, which would serve as a kind of landmark for the astronauts as they flew in so that they could navigate to the right site. Can we go to the next one, please? And this shows a close-up of the site. So this is the Apollo 12 backup landing site. And for some mysterious reason, it's never been illustrated before until I managed to figure it out. So, anybody could have done this, but it just happened to be me that did it. So anyway, that was the Apollo 12 backup landing site. And the astronauts would have landed in that, where I've got my dark spot there, and they would have been able to walk around and look at a couple of fresh craters there that had penetrated down into the bedrock just underneath the regolith, the lunar soil. Okay, let's move on, please. And there were countless studies of future Apollo sites as well. I'm not going to go through these in detail, but just dozens and dozens of studies of other places that Apollo might go, some of which people actually did visit, most of which they didn't. And even for the same site, there were multiple versions of what the mission might look like and what geological targets might be visited in the vicinity of that landing site. So this is just a sample of some of these things. On the left, it's the Marius Hills, volcanic domes. The second from the left is Tycho, this Surveyor 7 landing site on the rim of Tycho. Third from the left is the floor of Copernicus crater. And on the right, we've got Hadley Rill at the top 2, and then Rima Prince, a sinuous rill in Oceanus Procellarum. So sample missions there. Apollo 15 did go to Hadley Rill, but not to the site that's indicated there. Okay, next one, please. Now, let's move away from Apollo and from American things and look at the Soviet Union. I had to do quite a little bit of detective work to track down some of these things for Apollo, but that is nothing compared with trying to do this kind of thing for Russian data, believe me. So let's start off with something here. This area, which is right on the western edge of Oceanus Procellarum, it's just north of Cavalierius crater. This is the landing site of Luna 9, the very first robotic spacecraft that ever touched down safely on the moon and photographed its surroundings. And the actual landing site is right at the center of this view, just at the foot of those quite prominent mountains at the center. In fact, it might have landed right in the little valley between the 2 most prominent hills right at the center there. That's what you will find any place you go. Look in the reference books, go to the internet, whatever you find. The coordinates take you to that point. That's been marked on Russian maps. It's been marked on American maps. It's wrong. And how do we know it's wrong? Well, let's go to the next slide. This is the panorama, or part of the panorama, taken by that Russian spacecraft. And you can see that it shows a very flat horizon. But that horizon goes all the way from the south through the west to the north, slightly more than 180 degrees. And the whole of the left-hand side of that, if the old landing site was correct, the whole of the left-hand side of that would be a great big mountain. This would look, in fact, like the Apollo 17 landing site with mountains on one side of it instead of two. Big mountains. And they're not there. So the coordinates are wrong. Now, we shouldn't really be surprised that they're wrong because they just came from the Russian tracking data. The Russians tracked the signal of the lander as it approached the moon, and they said, oh, yeah, well, we think it's there. But those kinds of measurements come with uncertainties, and the uncertainties are on the order of 30 or 40 kilometers. That's quite a distance. But in this case, they have to be wrong because the mountains you would expect to see simply are not there. So let's go to the next slide, please. On this map, this is an American map of the site. I've shown the stated location of Luna 9 as the dark spot just on the edge of those mountains. They have to be far enough away from that site that those mountains are not even visible over the horizon. So they've got to be some significant distance away. And I've marked what I think is the probable location of Luna 9. Perhaps that circle could be a bit larger. The uncertainty could still be a bit greater. But it's got to be quite far away. So we can improve a little bit on Russian estimates of where their lander is. Can we go on, please? Let's try that for another mission. This is Lunokhod 1. It's the rover. It was the first rover, remotely controlled rover, that was put on the moon. Let's go on to the next one, please. And it photographed its surroundings, and lots of pictures were put together to make a map of the route that the rover followed. And so this is just a kind of shaded relief version of the Russian map of the travels of Lunokhod, the Russian rover. The biggest craters there, the 2 or 3 biggest craters just above center, are the only ones that we'd expect to see on photos in this area, because we don't have the highest resolution photos in this region. So let's go to the next slide. And this is the best picture that we have taken by Lunar Orbiter 4 in this region. And I've marked on it where I think Luna 17 probably is. Those craters that we were just looking at in the Soviet map, I think, are the ones indicated by the letter B there. Suppose that's wrong. Well, the fact is there just aren't very many other candidates. There are very few other places where we have craters with approximately that size and in the pattern established by that. So there aren't really other good candidates, so I think that might be it. And there is another little crater there that I've labelled A, which I think just might be visible as a very subtle little hill in the appropriate part of the horizon on pictures taken by that rover. Now, we don't really know that that's where Lunokhod is, but it's the best guess that we have at the moment. And we're really interested in knowing where it is because it carried a laser reflector. And the Apollo astronauts left laser reflectors at 3 sites, and the Russians put one at another site. But we'd really like to get laser reflections from this one as well. And but at the moment, we can't find it. And so this is an attempt to figure out where it is so that the lasers can be pointed in the right place. That work trying to contact it is still going on. Okay, next slide, please. And this goes on here. The Russians put 3 spacecraft into orbit around the moon to take pictures of the surface. And Luna 19 was one of these. So Luna 19 took pictures, and you look at these pictures, they're not really very good. They're rather weird-looking pictures, in fact. Luna 19 had a scanner. It looked, as it was flying over the surface of the moon, it would look out at the horizon on one side and then scan a line from the horizon all the way down underneath it and up to the other horizon. And then its orbital motion along its path would move it a bit, and then it would scan another line, and then another line, and so on. And it built up these rather peculiar pictures, which are looking out at the horizon on each side and directly down in the middle. And it's although these are somewhat oblique, it's the left and right sides that are looking out at the horizon here. So very few of these pictures have ever been published. Some of these are coming from the most obscure sources. take that one at the top. I found that in Izvestia, the Russian newspaper, the trade union newspaper published in the Soviet Union, which we have at Western on microfilm. So that's a picture that was printed in a newspaper, photographed onto microfilm, and I scanned it off the microfilm. So it's lost a little bit of quality along the way. But even so, these weren't great pictures to begin with. So anyway, we get the picture. Now, I want to know where that is on the moon. What I want to do is to make a map showing the photographic coverage of Luna 19. No one's ever done it before. I'd like to do it. I've done it for all the American missions in my book. I want to do it for the Russian ones as well. So where is this? So now imagine the difficulty of trying to figure out where that is on the moon, especially the lower one, which is such awful quality. Let's go on to the next one there. But we can take those pictures. A couple at the top show the sort of horizon-to-horizon geometry with the horizon at top and bottom on the left, truncated a bit on the right there. But they can be projected out into a proper map geometry. So down below I've done that. The one in the middle there is the top one from the previous slide, projected out into map geometry. And then you have the question of trying to find that. So you take those photos and you take a map of the moon, and you spend rather too long trying to find it. And eventually you track it down. So let's go to the next slide. So here we have a map showing the locations of the Luna 9 images. The only 5 images that we have. I was in Moscow, the Department of Lunar and Planetary Research at Sternberg State Astronomical Institute, talking to the head of the department, and I said, you know, could I see the pictures? Well, no, I don't think so, he said. Well, could I make a map that shows the areas that were photographed? Oh, well, I have to think about that, he said. Well, he's still thinking. So they didn't want to say. No, it's very difficult to get that kind of information. It's not really that it's secret or anything like that, but people were kind of afraid to take the step of releasing it. And I have sat in offices at Moscow State University with professors shouting at each other across the room, give it to him. No, if someone publishes it, it should be us. But you haven't done anything with it for 40 years. No, you know, going like that. And I never got the stuff. So it was very difficult to get that. So at the moment, what I can say is that this is the best indication that we have of the areas that were photographed. Now, one interesting thing about this is that if you read about Luna 19, you will read that the photographs were taken in this particular area. And the area is marked out as a white rectangle at the bottom of that map, but only a couple of the photos are in it. And the reason is that that came out of that same newspaper article in Izvestia that I mentioned. What it's really saying is this is where pictures were taken on this orbit, and that's just been taken in most accounts to mean this is where all the pictures were taken. But actually there are pictures well outside that area too. In principle, this spacecraft could have photographed long strips all the way from one terminator to another and out to the horizon on both sides. As far as we can tell, it didn't really do that. It may not have taken any other pictures than the ones we show here, or there might be a few, but we don't have them. A few others, we don't have them. So we still don't really know the whole story there, but it's difficult to get that. And just to make matters worse, let's go to Luna 22 and see what happened with that. So we'll go to the next one here. These are pictures taken by Luna 22, exactly the same thing, horizon to horizon, but this time we got quite long panoramic strips out of the mission, and so the top is one of the raw photos, and the bottom one has been reprojected to try to show the horizon areas a little better, although it's obviously quite distorted still. And any close students of the moon will recognize that area there. It's a little crater Torricelli at the right, almost all in shadow. Mare Tranquillitatis at the top, and Theophilus, the big crater at the bottom, right on the horizon actually, and rather distorted still in that view. So we get the pictures and we can plot them on a map. And let's go to the next slide, and we can see the photos. These pictures were not great quality, and these were actually taken after Apollo, when Apollo and the lunar orbiters and so on had taken fabulous pictures. These pictures were almost a waste of time. Why were they taken? They weren't taken to study the moon. These were experimental cameras being developed for spacecraft that could go to Mars, or perhaps to Mercury or asteroids or something like that in missions that never flew. Experimental cameras that were being tested at the moon. And this is one of the reasons why the Russians actually, they never did anything much with it. They had the data, but they never really published anything with it. And they recognize that the quality is really inferior to the American images, and that's one of the reasons why they're kind of embarrassed and won't release things now. At least this is the interpretation that we put on it today. So experimental data. But these do show the ground tracks of the spacecraft. It's photographing the strip underneath the orbiting spacecraft. So now let's go to the next slide. Luna 22 had an altimeter to measure the topography of the lunar surface. And here are 2 out of only 4 that were taken, altimeter traces across the surface of the moon. This is copied from a very obscure Russian journal. So where are these things? Well, luckily, we actually get the coordinates written at each end of the track so that we could plot them on a map. So let's see what that looks like when they're plotted. We'll go to the next picture. And this is a Russian map. I scanned this in Moscow. And this is going to be difficult to see unless you're quite close up to it. But there are actually several lines that are indicated with the Russian letter L and then 22. And those lines are at all sorts of strange orientations. Let me run across and point it. There's one of them going up there. There's another one there. There's one across there. There's one across there. Different orientations. I don't have a pointer with me, right? So different orientations. Those are supposed to be the altimeter traces. But the spacecraft is just orbiting in this nice little 20-degree inclination orbit. How can it be going in all these different directions? Well, let's go to the next slide. And this shows where those lines ought to be. That Russian map had the lines in the wrong place. And why? Because the coordinates, the way they were written, they didn't specify whether it was north or south latitude or east or west longitude. The person who plotted them had simply misread the numbers. Stupid, but there it is. Misread the numbers. But what does that tell us? It tells us that they never did any science with those numbers. They never took the altimeter trace and compared it with the craters underneath the ground track. Because as soon as you did that, you would see that it didn't match up. These match. I can see a trace right across the crater Ptolemaeus, for instance, in the appropriate altimeter trace. So now it matches. But theirs didn't. And they didn't because they didn't do the science. It wasn't intended as a scientific mission. It was pure engineering development to make instruments that could be used on Mars. And so I guess that's one of the things that we've learned about the Russian space program in the last little while as we've gotten into these things more. Can we go on, please? And I'm going to just finish off looking ahead a little bit to some future things. This is the south pole of the moon. The image in the background is made with Earth-based radar. This is from the big Arecibo radar instrument in Puerto Rico. It makes very high-resolution radar images now. We've got the system beautifully set up to take these kinds of pictures. South Pole's a funny place, right? The sun cannot shine on most of the areas that are illuminated here because the sun can only rise about 1.5 degrees above the horizon right at the pole. But the Earth can rise about 5.5 or so degrees above the horizon. If any of you are lunar observers, I know some of you are, then you'll see that this is in fact the corollary of what we call libration. The moon appears to wobble a little bit, and especially there's a north-south libration, so sometimes we can actually get quite a good view of the north pole of the moon, but the south pole's tilted away from us a bit. At other times we can see the south pole quite well, but the north pole is pointed away from us a bit. So if you now reverse that, so you're on the moon, sometimes if you're at the south pole, the Earth will be a few degrees above the horizon, and sometimes it'll be a few degrees below. So, and actually the Earth can get about 4 degrees higher above the horizon than the sun ever can. So it illuminates some places that the sun can't shine into. So that's what's happening here. Quite a lot of these areas are never in sunlight, but can be imaged by radar. And I've just marked on a few candidate places. But what I would like to say is that if everything went according to plan, there was a new impact in this area, approximately here, approximately there on the rim of that crater Shackleton, by the Moon Impact Probe on the Indian spacecraft Chandrayaan-1. that should have happened today. Okay, so let's go on. That South Polar crater has been picked by NASA as a possible place for an outpost, and this is a map of the little place on the rim of Shackleton Crater, showing the area that they're interested in. It's not permanently illuminated. People have often talked about a peak of eternal light at the pole that is always illuminated. There isn't